Building an engine. Why is a new engine built? The demand originates with the commercial department. The success of their sales efforts produces more passengers and parcels, and the operating department has to produce longer trains to carry them. Longer trains demand bigger and better engines, and moreover, engines that can work economically. Today, an express engine has to work at high average speeds over long distances with heavy loads of 500 tons and more, exacting requirements for an exacting task. This is where the chief mechanical engineer comes in. He has to design and produce the engine. The new engine makes its first appearance on paper. Over 370 drawings of the several parts have to be thought out and prepared, each one being passed by Mr. W.A. Stanier, the chief mechanical engineer. Plans approved, a specification is prepared, a volume that runs to 361 pages and contains over 2,500 items. From this specification, orders are issued by the stores department, and many are the industries that benefit thereby. In due time, material starts arriving at the works. The main frames, which may be called the foundations of the engine, arrive in the form of flat steel plates, each 1 1/8 inches thick and weighing 3 tons. The first process is cutting them to the desired pattern. Oxy-coal gas cutters, working automatically, trace the pattern on the steel plates, guided by the template. Rather like dressmaking, isn't it? Next, the slotting machine. This huge piece of mechanism, weighing 100 tons, eats through 10 plates at a time. Each tool is operated by a 20 horsepower motor. Drilling the plates to take the various rivets and bolts is done by a multi-boring machine, which drills any size of hole up to a diameter of 3 to 4 inches. Cutting, slotting, drilling, and the final trimming reduces the weight from 3 tons to 2 1/4. Now the frame is ready for assembly. Carefully the plate is guided into position alongside its twin, to which it will be securely fixed, ready to receive the cylinders, whose manufacture is dealt with in the next chapter of our story. Over 60 molds and cores are required to make a pair of inside cylinders for our engine. Skilled workmen fashion them in sand from patterns made of wood in a nearby shop. Foundry work is rather paradoxical. It's what isn't there that matters. A mold eventually consists of an ordered assembly of spaces into which the molten metal is poured to form the article being manufactured. One by one, the pieces are lowered into the mold. The assembly of the cores in this mold is a task something like fitting together a giant jigsaw puzzle. But in this case, the men know where all the pieces go. The molds and cores, being made of sand, need the utmost care in handling. A 12 hours drying causes the sand to assume a consistency almost as hard as cement, though of course much more brittle and porous. This enables the sand to withstand the great pressure of metal soon to be placed upon it. Casting time is an anxious time in the iron foundry. The cupola has to be tapped at precisely the right moment, and the 4 tons of white-hot seething metal taken to the site of the cast in the shortest possible space of time. The critical moment arrives. Over she goes. The aperture into which the metal is poured goes by the name of the runner box. It acts as a sort of funnel. The foundry foreman takes up his position and, carefully watching, gives the signal to pull out the plugs. Immediately the cast is complete. This allows the gases given off by the hot metal to escape. Metal may set too quickly near these plug holes, and these men, carrying out an operation called feeding, are preventing this from happening. By this process, the metal is fed to the mold, preventing blowholes from forming, which are likely to spoil the rust. After casting, the cupola is cleaned, ready for the next charge of metal. One or 2 days to cool, and the mold is ready for breaking open. A crane, fixed to the actual cylinders, draws them away from the molding boxes. Men with crowbars break away the sand so carefully and skillfully fashioned by the molders. Pretty hard life for the molders. All his work seems to end in dust. The true shape and size of the cylinders is at last revealed. A piece of modern precision mechanism made, one almost might say, out of some sand, a few boxes, and molten metal. Hats off to the foundryman. Leaving the foundry with its glare and dust and smoke, we'll follow our cylinders to their next port of call, the heavy machine shop. The first operation in machining the cylinder is milling the sides. Boring the cylinders is a tedious, though highly important job. The degree of accuracy demanded is of an exceptionally high order. Holes are drilled to take the securing bolts, and this machine is making a slot in what appropriately enough is called the saddle, on which the smoke box will be fixed. Now for our first bit of real engine building. Completed cylinders meet the completed main frames. Add the 2 outside cylinders, which have gone through exactly the same process as the inside cylinders, and the frames are ready to leave for the erecting shop. For the journey, the frames are mounted on temporary wheels. Immediately they arrive at the erecting shop, they are transferred onto jacks in position number 1 on the erecting line. Machinery does not everywhere reign supreme. Here in the smithy, the merry ring of the anvil can still be heard, and brawny arms wielding the hammer still strike sparks from glowing metal. In the midst of modernity, the ancient craft of the smith still holds a place. Weight, of course, is useful in the smithy, and we've no hesitation in affirming that the smith a mighty man is he, because we've got proof. All manner of smaller parts are made in the smithy. Nuts and bolts in all sizes and varieties, rivets by the tens of thousands, washers, springs and small forgings. They're all part of the grist that comes to the smithy mill. To many of you, a boiler is just the round barrel part seen on any engine running about the line. but many and varied are the mysteries concealed beneath its rounded sides. The plate just going into the furnace is the bottom half of the throat plate, or the saddle plate as it's sometimes called. Its purpose is to join the barrel to the firebox. The oil-fired furnace soon brings the plate to the required heat, and it is craned rapidly to this huge press, capable of exerting a pressure of 700 tons. The blocks between which the plate is squeezed themselves weigh 41 tons. Crewmen are proud of this job. It's the largest pressing yet made in the works. This plate is the tube plate. It supports the smoke and superheater tubes at the smoke box end of the engine. Batteries of machines, each designed to do a particular job, cut and drill the various parts of the boiler, steering through the tough steel as though it were cheese, until finally they are ready to be assembled. This gigantic machine applies little more than gentle pressure to force into shape the steel wrapper plates. By the time it has finished its job, the sheet of metal will have assumed the shape that you will see here. This, as you see, as the outside of the firebox in a finished engine. Inside the steel wrapper plate is suspended, as it were, a copper firebox. It is this copper firebox in which the fire is actually made. First in the assembly of the boiler is the joining together of the three sections of the barrel. Here you see the various parts of the boiler laid out in line. Steel wrapper plate, foundation ring, top and bottom half throat plates, fire door plate, and the barrel. The throat plate, which you saw in the press, is being attached to the barrel. Some 3,500 rivet holes have to be drilled. On this tower triple drill, the boiler can be rotated, moved backwards and forwards, and the drilling head moved upwards and downwards. The gigantic size of the boiler can be realized from this picture. The rotation of the boiler on this tower riveter, though not power operated, is extremely simple. Rivets, rivets, and more rivets, adding strength to strength. 250 pounds of pressure to the square inch needs a bit of holding, and hold it the boiler must. The inside copper firebox and the outer steel casing are securely held together by over 2,500 stays. The stays are screwed in and the heads riveted over. This job looks difficult, doesn't it? But years of practice make it one of comparative ease to the boiler makers. We will say goodbye to the deafening noise of the boiler shop, and also, for the moment, to our boiler. Quite a lot of brass, metal I mean, not money, goes to the making of an engine. Most of the cab fittings are made of it. Injector gear, innumerable bushes of varying sizes, all sorts of connections such as elbows and T-pieces, valves, set screws and nuts, washout plugs, to name only a few, all these are made of brass. Practically all the brass work required is cast in the works at the nearby foundry, the process being exactly similar to that carried out in the iron foundry or in any other metal foundry for that matter. This is where the mysteries go in. A modern engine, such as 6207, has a big appetite for steam, hence her large grate area of 45 square feet and her high amount of tubing. First to go in is the main steam pipe, through the center of which will later go the rod connecting the regulator handle to the valve. Now the smoke tubes, of which there are 112, each 19 feet 6 inches long. The 32 superheater tubes are the same length. As you will see, these are screwed to the firebox tube plate. If you care to work it out, number 6207 carries over 2,700 feet of tubing. Meanwhile, things have been happening at the other end of the boiler, and some familiar objects have been finding their way onto the fire door plate. No need to tell you what this is. The boiler is almost ready for testing. Before we actually see it under steam, do you know what happens when the driver opens his regulator? Watch. Under steam for the first time. Previously, the boiler has had a stringent hydraulic test. There are two steam tests, the first at 10 pounds over normal pressure and the second at normal pressure. And if that boiler leaks, the shop foreman will promise to swallow it, tubes and all. One more process and we are finished with our boiler. Heat is precious and has to be conserved, and this is how it's done. The aluminium foil is quite a recent discovery in this lagging process. It has been found to possess remarkable heat-resisting properties. With the fixing of the lagging sheets, the boiler is really beginning to look like a boiler, and it now only remains to mount it on the frames waiting to receive it. One of the most amazing sights is the way heavy loads, and mostly awkward and cumbersome ones, are slung about in the works. A screech from the overhead crane, grappling hooks descending out of the air en route, and almost before you can say knife, a load of from 50 tons up to a complete engine is whisked away to a new position. As we're in the erecting shop, we'll stay long enough to watch one or two familiar objects being fitted. Every one of you will recognize the engine cab. Looks very much bigger in mid-air than it does on the engine, doesn't it? At this stage, too, we'll add another familiar feature, the number. It only needs this, and 6207 is really beginning to look like an engine. We leave the fitters to get on with our job, while we take a look in at the steel foundry. Its time 6207 had some wheels. The mould that forms the wheel is made in two halves. Sand is placed round the first half pattern, well rammed to fill all the crevices and corners. The process is much the same as that followed in making the cylinders. The pattern rammed up, the hole is turned. Over she goes. Now remove the baseboard. Out comes the pattern of half the wheel, to leave a perfect replica of itself in sand. Now the other half. Stand round the pattern again. Place the top on the mould and turn the whole over. Quite spectacular, these twists, aren't they? Remove the pattern, leaving the imprint of the second half in the sand. After being dried for 12 hours to harden the sand, the cores are inserted. Now the two halves of the mould are joined together. The moulding boxes are clamped together and our wheel is ready for casting. Molten steel looks hotter and, as a matter of fact, is hotter than molten iron. In the steel foundry, the ladle travels on a sort of overhead railway, and when it comes opposite the mould, the metal is released. A few hours to cool, and the mould is ready for breaking open. And so a wheel is born. To its making has gone 3,500 weight of the finest steel, and the skill and experience of the steel foundryman. Before it leaves the foundry, the wheel is dressed and fettled, and the surplus metal is removed. The next time we see our wheel, it will be in the wheel shop, and here it is. This machine makes 3 cutting actions simultaneously, turning the rim, facing the boss, and boring the boss. Seems to treat the tough steel almost with disdain. After the machining has been completed, the wheels are mounted on the wheel press, which joins them to the axle. Meantime, the axle, a crank axle this one, is being machined and is practically ready to join the wheels on the press. First, mount the second wheel. Now we're ready for the axle. In pressing the wheels onto the axle, this machine exerts a pressure of 150 tons, so that there is no fear that wheel and axle will ever part company. We've speeded up the action so we can see just what happens. Normally it's a 5 minutes job. Next, the wheels are ready for tiring. Heating the tire, which you see lying on the ground, causes it to expand, so that the wheel center fits into it quite easily. At normal temperatures, the tire is 1/16 of an inch less in diameter than the wheel center. As the tire cools down, it shrinks firmly and securely onto the wheel center. The tire is rolled onto a retaining ring, and our pair of wheels are ready for balancing. True running demands a perfectly balanced wheel. Rotated at high speed, faults soon disclose themselves. Watch the oscillation of the bolt on the top center of the picture. Now to correct it. Add a temporary weight. Start the machine up again. And watch the bolt now, as steady as a rock, at a speed equal to 65 miles an hour on the track. Weights equal to the temporary ones, fixed to the wheels, keep them perfectly and permanently balanced. 6207 is now ready for wheeling. Actually, the engine is placed on the wheels and not the wheels on the engine. Two 50-ton cranes lift 6207 and move her to a position over the wheel. The 3 driving wheels are fitted first. The 4 leading bogie and 2 trailing wheels will come later. Slowly and carefully the engine is lowered. Men on either side and underneath guiding the wheels. A tricky operation this, where more haste definitely means less speed. Our next job will be to provide the motion. The various parts of the motion, which if you do not know can best be described as the moving machinery, start life in either the drop forge or the heavy forge. There is a difference between the two forges. In the drop forge, which you are seeing, the article being manufactured is stamped out in a shaped die. In the heavy forge, the article is shaped largely by the skill of the smith. These men are making a combination lever. A machine trims off the surplus metal and the job is finished. A connecting rod enters the heavy forge as a rectangular block of steel weighing 12 hundredweight. No ring about this anvil. 8 tons of steel hammer descending on steel billet thuds solidly. The iron floor trembles at the impact. Thud goes the hammer. Hand iron machine in perfect unison, shaping, squeezing, forcing the reluctant metal to the will of the hammer and to the will of the men of the forge. The charge hand is the brain of the hammer. It is he who signals to the man who operates the hammer the strength of the blow required. There must be, perfect understanding between the two. It takes but 5 heats to forge a connecting rod. 5 times into the fire, 5 times under the hammer. The maximum amount of work must be done at each heat to complete this amazing achievement, so that the men of the forge must be both quick and sure. See how near the forged rod is to the template. Who will say now that the day of the craftsman is no more? We leave the heavy forge, and with the connecting rod, enter the hum and clatter of the machine shop. Machining the flats is the first operation, a process that gives a glass-like surface to our rods. To reduce the weight of the rods, the sides are fluted, and this is the machine that does the job. Circling the ends, the official phraseology, seems to provide an adequate description of this operation. As you see, this specially designed machine smooths the rounded end of the rod. Holes have to be bored at either end of the rod to take the bushes. This recently installed machine is the latest of its type for doing this class of work. The rods bored, the bushes are pressed home. These rotating burnishers give a super finish to the connecting rod, as well as taking off all the sharp edges. This process completed, the rod is ready to be fitted to the engine. Before, however, we actually do so, let us see exactly where the combination lever goes. Since leaving the drop forge, it too has been machined and is now ready for fitting. Now for the connecting rod. As I'm sure you all know, the connecting rod joins the piston to the driving wheel, so that by it the power is transmitted from the cylinders to the wheels. Little work remains to be done to complete 6207. Must have a tender for her though, so let's take a look at the tender shop. The 2 parts of a tender, the frame and the tank, are built up simultaneously on adjacent roads. On the right-hand side is the tank, on the left, the frame. As the pictures follow one another, you can see the tender grow. Watch. Right-hand side tank, Left-hand side frame. Right tank. Left frame. At the end of the line, the two parts come together. The tank being mounted on the frames and the finished tender, capable of holding 4,000 gallons of water and 9 tons of coal, is ready to join the engine. Although Crewe Works recently celebrated the building of her 6,000th engine, the birth of a new one still holds a thrill. Here she comes. Latest of her class, pride of the line and pride of the men who built her. Over 90 years of experience has gone to her making, for it was in 1843 that works were first established at Crewe. Dead and lifeless as yet, steel hawsers draw her slowly into the open. 6207 is an engine worth being proud of. An engine you can boast about with safety. Soon she will be rushing over the main lines at 80 miles an hour, hauling trains of 500 tons or more. But first, let's introduce her to her tender. Finally, 6207 has to undergo a strict and rigid test. The vacuum brake is tried. Boiler pressure okay. Safety valves blowing off at the right pressure. Cylinder cocks in order. Injectors working. Whistle. And lastly, regulator handle. She's off. A 1,000 men have served her in the making. How many thousands will she serve during her life on the LMS main line? Efficient service follows efficient workmanship. That is a lesson we can all take to heart, whatever our job may be. 6207 is finished. A British product made throughout of British material by British workmen. Here's to you, 6207. Good luck and good running.